This is the third electromagnetism video for A-level physics. The aim of this video is to consider magnetic flux when the angle between the magnetic field and the loop that it's passing through vary. First, let's consider the arrangement that we've been going over generally, and that is the loop sitting inside a magnetic field that it's perpendicular to. So we'll draw that out. Here is our magnetic field represented by the red crosses inside circles, so we're talking about a field that's directed into the page. The white rectangle is the loop that we're interested in. We're interested in the flux through that loop. Okay, we can also draw this in another view. We can take a side-on view. So what we're really interested in this case is looking end-on, looking at that edge there. So if we look at that edge and place this into the magnetic field, we've got three field lines passing through the loop that we can see. We can imagine that if the loop was rotated, the flux through the loop would change. We're going to rotate the loop around this point here, which on this diagram to the left would be rotating along this axis here. We'll rotate it around like that. So this is turning around like that. Eventually the loop would end up, if we turned it through 90 degrees, in this position here. In that case we see that no flux passes through the loop. We've got two cases here: loop with full flux, and the second case when the loop's been turned through 90 degrees, loop with zero flux. This picture here on the right doesn't make it as easy to see as possible. We can draw a better diagram and get a closer look at this. Okay, so if we draw that diagram, here is our more detailed field. We can see that this field is directed to the right and it's uniform. We know it's uniform because the field lines are evenly spaced. Let's place a loop into this field. So we'll place the loop in this sort of view, the end-on view. So this is like the second view we had. So it's just like this one, but with more detail. We're also going to rotate that loop around some central axis. So place an axis right there. We're going to rotate this around that axis. So sometime later, once we've had a chance to rotate this, the loop might well look like that. So still with the same center right there, and the loop's been rotated to some angle. If we put that angle in, just draw a dashed line. So it used to be in that position following that dashed line, and it's now been rotated through some angle theta there. We can see immediately that the amount of flux through this loop must have decreased. If we go through and check off field lines here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 field lines, so that relates to some amount of flux. And here, where the loop has been rotated, we've got 1, 2, 3, 4, 5, 6 field lines passing through the loop. So we've gone from 10 to 6. If we've decreased the number of field lines going through a loop, we've definitely decreased the flux, because in videos 1 and 2 we've established the idea that magnetic flux is just a measure of the number of field lines, or the amount of field that passes through a loop. So we've gone from 10 lines to 6, so we've got a drop in magnetic flux. We also established in video 2 that flux is calculated in the following way. Flux, which we represent as phi, is BA. magnetic field strength, B, multiplied by area of the loop. Well, the original, the loop itself here has some height and some width to it. It's got a height h and it's got a width w, like that. We can see on this picture here, if we extend out some dashed lines, we will need some space on the picture, that that's h, right, if that was also h. What would be more helpful to focus on is the area that the field lines actually pass through. So we'll draw what we might refer to as an effective loop behind this. Just making that line a bit thicker. All the field lines that pass through our rotated loop, so these ones that I'm going to go over in green, also pass through our effective loop. And our effective loop is just a lot easier to think about. There's no angle there to deal with. Let's try and establish the area of the effective loop. So the effective loop, we draw out this triangle. We've got h and then our effective loop. And we have an angle in here, theta. So this must also be theta here. So we're looking at h cos theta. If we were to draw out this loop in this type of view, the face-on view, the head-on view, it would look like this. It wouldn't be as tall as the original loop, but it would have the same width. So it's still w in width, but it has a height of h cos theta. And this is the face that takes all of the field lines through it, all of the flux. If we refer back to phi equals BA, the magnetic field strength hasn't changed, so we can still write B for the field strength. But the area has. The area is now WH cos theta. If we look back at this loop here, we'll say that the area of this is A. So we're saying that A equals WH. That means that we can replace this part of our equation by just writing A. So phi equals BA cos theta, where theta is the angle between the loop and the normal, so perpendicular to the field line. Okay, just to draw that out, just to be completely clear, here's our rotated loop. Here are our magnetic field lines passing through that loop from left to right. Just put arrows on these. The angle of rotation is the angle theta there. So we're talking about the line that's perpendicular to the field lines and the line of the loop itself. That's where this angle is trapped. That's what it's formed by. So it's between these green lines here. That's what's stated just there. Okay, that's how we calculate the flux through a loop that is rotated to some angle.